that transform that does this instead of that. Yeah. So, I mean, if you wanted to map it onto geometry, instead of mapping onto, say, the surface of a sphere like Newtonian, this maps onto a hyperbolic surface. And that's where the negative sign comes from. So it's a little weird. So that's the dot product. We'll use that maybe once on Thursday. All right. So what I want to do now, though, I was able to get my CT and X in terms of these others. So what I want to do, though, at the top of that third page, instead of CT and X, I want to use C dt and C dt and dx, and get out C dt and dx in the new frame. Okay? So, and then I want to write those, the dx on the top and the dy on the bottom. So go on ahead and work that out. Find another board. All right, so dx over c dt, and that's okay. I mean, it's basically just these guys except with d's in front of the coordinates, right? Yeah. And if we write them in the fraction here, what happens with all those gammas?
They all cancel.
Yeah, they all divide out. Okay, so all those gammas are going to divide out, and you will then have, let's see, dx on top. So I'm going to get beta c dt prime plus dx prime, and then on the bottom we're going to get c dt prime plus beta dx prime, having left all the gammas off. Yeah, since that's an overall scale factor, it makes sense that it divides out.
Wait, everything is prime in this?
Hmm?
Oh, it's a bit, sorry. I didn't realize because it was adding, I thought it would all divide out.
Yeah, you've got gammas on top and bottom, they all go away. All right, and so now I said from there, we're now going to divide top and bottom by c dt prime. All right, so that'll leave beta there, and a 1 here. Okay. And I'll let you do the rest of that, see what you come up with. So what else do I have on top here?
dx.
dx divided by c dt prime.
And
dx.
same thing here? right?
Should the dx in the denominator have
Hmm?
a prime?
Okay. So what you've just done is you've come up with the velocity addition formula for special relativity. So our velocity in the new frame, so equals this stuff, so that's beta plus, I'm gonna use and this is if I'm using U, I have to use it consistently here. All right. Especially when you're starting out, I like to use U as particle velocities and reserve the V for the frame velocity, so that it doesn't get mixed up.
Is that a beta or a beta U?
Hmm?
Is that a beta or a P?
That's a beta,
So you have to add them and then divide by 1 plus the product?
yeah.
Oh.
Okay. So that's what the velocity addition formula gives you. That doesn't look anything like what we did in Newtonian physics. What did we do in Newtonian physics? That. This is a whole new ball of wax here, all right? Now, if, let's see here, so if we go to the limit where the velocity between frames, or the beta between frames, is much, much less than 1, all right? So beta is much, much less than 1 here,
And then P times P is basically 0.
yeah.
Just adding again.
So, I mean, yeah, that gives me a little bit of a problem here. I've got 1 plus this. It's not really easy to do that here. Yeah, I'm not gonna try and drag, I'm just looking at the clock, I'm not gonna try and drag you through that, because this one's a little bit messy to work through the limit. With a lot of these things, when we get a result, if you look at this limit, it should reduce down to the Newtonian result. So, I mean, it should reduce down to something like that. But I'm not gonna try and do that here. So I'll not go there. So let's look at our questions here. So first one, I have a pulsar out there that sends out a beam of X-rays going in opposite directions here. Those are electromagnetic radiations, those travel at the speed of light, all right? They go in opposite directions, and I want to know, so I know that, let me see here. I know that in pulsar's frame, U is equal to C, and I'll use beta is equal to minus C. Okay. So in other words, here's my pulsar, here are my gammas. So this is U, and this is going to be U over C. This was crazy. Beta is -1, and that means that beta U is 1. Okay, sorry. Yeah, so I'm gonna have U this way, I'm gonna have minus U that way, or minus C, I should say. We know that's what it is. And then, yeah, so beta U is 1, and beta is -1. So we're going to put it in there and find out what we get for, I guess, this beta U prime. Okay.
0,
So we're going to put it in here and see what we get.
0.
Let's see.
You get 0 divided by 0.
Yeah, let me make sure which way we're going here.
Why does beta become -1?
So the pulsar frame, this light ray is going out with in the plus direction, so beta's 1. This was going the minus direction, so beta's a -1.
But it's beta times negative c, so it's just plus 1.
So what I'm trying to go to though is I'm gonna go from here to, I'm gonna go to this X-rays frame. So in this X-rays frame, this X-ray was moving at -c relative to pulsar. So in this frame, the pulsar is moving at,
Plus c?
yeah, so you see, beta pulsar is going to be +1, all right, which is, C over C. And then this one is gonna be something faster yet. This one's gonna come out to be beta U. Okay. In the pulsar frame, it was 1. Not sure what it was here. So this is beta U prime is 1. And then beta for the frame switch here is also gonna be 1.
So which betas are we putting into the formula?
We'll be using, what?
So you add them together?
Yeah, because remember, to go to this frame, basically I look at the velocity of this in this frame is the velocity that it had in the old frame plus the velocity of the frame, which was
Plus 1.
+1.
So, wait, what does beta U represent again?
Hmm?
What does beta U represent?
That's the V over C for this X-ray over here. So the pulsar frame, it's just C over C. In this frame, it'll be something bigger than that. Well, it'll be something anyway. And so the tricky part is figuring out, oh yeah, we want to look at it in this frame, in which case, to go to this frame, I'm now boosting that by the speed of light.
You just get 1.
Yeah. So I get 1 plus 1 over 1 plus 1 times 1,
Which is
Is
also
1.
1. So that's 2 over 2,
Yeah.
which is 1.
which agrees with the speed of light is the same
So
for all
they're
observers.
moving at the same speed,
Yeah,
both the pulsar and the X-ray.
yeah. We won't mention the fact at the moment that having the pulsar itself move at the speed of light is a little problematic, but
Oh,
Yeah.
true.
we'll worry about that on Thursday.
Would the X-ray be like bunched into the pulsar at that point? Or?
No,
Oh, because of the.
So-
Every pulse would be emitted at a different location.
yeah,
So it's just pulsar.
yeah.
Actually at the same location, so they don't build up.
If we're gonna apply that again, I have an electron moving at 0.992 C, collides head-on with a positron, moving at 0.981 C. And both speeds are measured relative to the lab. Let's see here.
Does light experience time?
Hmm?
Does light experience time?
No. Which is weird. As far as light's concerned, delta T is 0 all the time.
How does it change in frequency and such then?
It doesn't. I mean, it's not gonna change the frequency unless it interacts with something, and those interactions are gonna have all kinds of things coming in. But if you just have a traveling light ray, the phase, the sign plot is the same all the time. Now, the outside world is moving by it, whatever, but it's sitting there. I don't see any changes. All right, so we have these two velocities. I'm just trying to see whether it was, it looks like they're in the same direction. Yeah, so these must be moving in the same direction.
They are?
I think. shift. Oh, head on, no, they have to be on, sorry, they have to be in opposite directions, head on. Yeah. Okay, so you have, what do we have here? 0.992C. And this one's coming that way at 0.981C. You're gonna go to a new frame, which is at rest.
So then you have to add the speed of the frame to every other object.
Yeah,
Gotcha.
yeah. So normally, you just add this to 0 and add this to that, which gives us some problems. It's the second one that we have to use our fifth one. And since these are in the same direction, you know, just leave the sign off, you know, it's gonna be that way. So you have 0.992 plus 0.981 over 1 plus the product of those two.
Gives you a lot of height.
Yeah.
I wish I could not see the picture.
And then if you do the speed of the electron in the positron's frame, so it's gonna go the other way, well,
Can you just put a negative sign on it?
yeah, I mean, there's gonna be a negative sign, and then, you know, basically these switch and these switch, and it's the same thing. Yeah. All right. All right. So, didn't get to where I wanted to get to, but we got. So, on 10, we'll start with that, I guess, on Thursday. And on 10, we're actually gonna use what we've gotten so far to drop out the redshift from relativity. So there's a relativistic redshift involved. And then the next page is getting you started in on momentum, which is really for Thursday. We also didn't get to the magnetism and relativity. I want to do a demo for you before we break on that, and then call it good. So let me, quick here, I'll take a second. Okay, so light's glowing, right?
Yes, sir.
That means I have current through the wires, do I not?
Yeah.
All right, now,
That'd be magic.
you remember this guy? What did I use that to tell me about?
Charge?
Charge, right? Okay, so I have current flowing through this wire, so you can see it there, and I break this right over it, and what's my net charge?
0.
Zip. So a current carrying wire has no net charge in it. That's going to be important for our magnetism or relativity one, right? So the magnetism or relativity, you're going to look at a current flowing through a wire. We're going to just say, I'm not going to deal with all the minus signs. We'll have positrons moving in the direction of the current, and a positively charged particle outside moving at the same speed along the wire, in parallel to the wire. So the current in the wire will generate what?
A magnetic field.
A magnetic field. And a moving charge in the magnetic field will experience a Lorentz force, and that's easy enough to calculate. The next thing we're going to look at is the charge densities in the wire. Now, since there's no net charge, the positive and negative charges in there must be distributed with equal density. So they cancel. Then we're going to transform the whole thing, the Lorentz transform, into the frame of the particle outside. So we're going to go its rest frame. That means now that the wire is moving oppositely, so I have a velocity, and I'm going to then have to change my spacings, my densities there, and so on. In the original frame, I had the same density, but my positive charges were moving in that frame. In the new frame, the positive charges will come to rest, and now the negative charges are moving in the other direction. that's gonna give us an unbalance in the density. And since I have a charge imbalance, what do I have around the wire now? An electric field, which we'll calculate, go through, all the symbols, and what we'll find out is how does that magnetic force on the moving charge compare to the electric force in the new frame?
They're probably the same.
And we'll see what we get. So that's the gist of what we're gonna do with that one. So I'm hoping to get that one and, you know, the rest of this a little bit, in there on Thursday, okay? But once again, your anchors here, you know, are this, and then our Lorentz transform from one frame to another with, yeah. Okay, so those are the things. We're gonna take that and look at momentum conservation on Thursday. So I'm gonna actually have you derive what the momentum four vector is, just from Lorentz transformation, and the idea that if we go to very small values of beta, it should recover Newtonian physics. Okay. And that'll be enough for us to figure out the four vector. There's more on the energy relations, which Einstein dropped out, and I'm not gonna go through those in the lecture, but we'll use them. And we'll look at what goes on with that on Thursday. Okay? Yeah. All right. You guys are amazing.